Questions 21 through 25 on the 2010 Grade 10 AMC 10B. A palindrome between 1,000 and 10,000 is chosen at random. What is the probability that it is divisible by 7? So let's just list a few to get an understanding. When you have the ones with 1,000 to 1999, they'll all be of the form like this. 1, 2, 2, 1, and so on, right? All the way down to 1, 7, 7, 1, 1, 8, 8, 1, 1, 9, 9, 1. And then we get into the next category, which is, of course, 2002, and then 2, 1, 1, 2, 2, 2, 2, 2, and then you just keep going like that, dot, 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 and you get eventually to 2, 7, 7, 2, 2, 8, 8, 2, and 2, 9, 9, 2, right? So this just keeps going like this, and you get the idea. At the very end, it'll be 9002, and so on. Now, how many, first and foremost, are there? Well, in this column right here, as you can clearly see, there's 10, right? And similarly 10, and then it just keeps on going. For each of those columns, it'll be 10. So in total, there will be 90. Now, the calculators are not allowed on the American math competitions, so we can't plug these in and divide by 7, and that would take a long time since there's 90 of them. So there's got to be some quick system. And there is some good news. That first number, right off the bat, this guy, is divisible by 7. So that definitely helps. Since 1001 divided by 7 is 143. So there you go. And then if you can notice that every single one of these numbers is essentially of the form 1001 times some number a, plus you're just adding 110 every time. So 110n, right? Because if you look at these numbers, they're always just adding 110. I hope you can see that. 1001 plus 110 is the next number. Then you add 110, you get the next number, and so on. So every number is of this form. So if this is divisible by 7, which it is, since I just showed you that, then any number of that form, which essentially describes all the numbers, is going to be divisible by 7 if this is divisible by 7. And first and foremost, let's see if 110 is divisible by 7, and it is not. 110 divisible by 7 is like 15 point something, 15.7 I think. Okay, no problem. That means n must be divisible by 7. So, more good news in this question is that we really only have to concentrate on one column, because all the columns behave exactly the same. For example, the first column, A is 1, and then you just go up by 110s. And the only one that's divisible is when n equals 7, right? Or when n equals 0. But that one I just talked about right here. The only other one is when n equals 7, and that is this guy right here. So I'll just circle the ones that are divisible by 7, this one and this one. And if you can look at it in this format, it makes it very clear why. And for each of these columns, there's going to be 2 that are divisible by 7. That one and that one. And this one, that one, and this one. So since each column has 10, and of the 10, 2 are divisible by 7, 2 out of the 10 will be divisible by 7. And that's true of all the columns. So the probability, in lowest terms, is 1 over 5. So number 21, the answer is E. 7 distinct pieces of candy are to be distributed among 3 bags. The red bag, the blue bag, must each receive at least 1 piece of candy. The white bag may remain empty. How many arrangements are possible? We have 7 colorful pieces of candy, and we have 3 bags, right? So we've got, what are the colors here? A red bag, and we have a blue bag, and then we have a white bag. Now, they want us to figure out what is the probability of all, or how many arrangements are there? Not really a probability. Okay, so we have to look at this in a kind of a different way. The way I'm going to look at this is, first I'm going to figure out the total number of ways to do this without any restrictions. And then from that I have to subtract if the red bag is empty, and I'll explain this, and the blue bag is empty. So let's explain this first and foremost. First, let's talk about this where there's no restrictions. So you can put the candies anywhere. If that is the case, for candy number 1, I have 3 choices, either the red bag, the blue bag, or the white bag. For candy number 2, I have again 3 choices, and similarly, there will be 3 choices for every single one of these candies. And you multiply them all to get the total number of combinations, and that is 3 to the power of 7. So that represents the total possible arrangements when there's no restrictions. Now we have some restrictions. Ours are as follows: that the red bag and the blue bag must have at least 1 piece of candy. Okay, so what I'm going to do is look at a scenario where the red bag is empty. Because if I figure that out and subtract it from the total, it will only have scenarios where the red bag has at least 1 candy. So I hope that makes sense. So the scenario where the red bag is completely empty means that for candy number 1, you only have 2 choices this time. You can't put it in the red bag because we want the red bag to be empty. So for candy number 1, we have only either a blue bag or a white bag. Candy number 2, we have only a blue bag or a white bag, and similarly, all of these will be 2s. So this is 2 to the power of 7. So this red bag being empty is 2 to the power of 7. And in a very identical way, the blue bag being empty also is 2 to the power of 7. But that doesn't completely finish the scenario. There's also a scenario where both are empty, right? So we have kind of double counted that. We have to subtract that. Both are empty. That means all the candies are in the white bag. And if all the candies are in the white bag, there's only one way of doing that, of course, is putting all 7 in one in the white bag. So I have to subtract that from that. Because red empty, blue empty, if you put them together, there's one scenario where both are empty. Correct? So that was double counted, so I have to subtract it. Okay, so I hope that makes sense. So this is it. This is the probability. It really boils down to just this equation. So if you do the math here, if you figure out all these numbers, it comes to 1932. And I want to point out one little thing here. Note that this number of 1932 is the only number in the answer choices that is divisible by 42. And that's important. 42 represents the number of ways that you can get 2 candies from 7 different candies. So if you're choosing the first one, you have 7 possible choices, and if you're choosing the second one, 6 possible choices, and that equals 42. So you know somehow, some way, that one of the answer choices has got to be some multiple of 42. And I don't know if that helps you or not, but I just wanted to point that out. So number 22, the answer is C. The entries in a 3 by 3 array include all the digits from 1 to 9 arranged so that the entries in every row and column are in increasing order. How many such arrays are there? So we have 3 scenarios. The first scenario is when you have a 4 in the middle. So the middle number will be 4. The second scenario is when the middle number is a 5. And the third scenario is where the middle number is a 6. Now, the important thing is that if I were to draw this, you will notice that the 1 and the 9 always have to go in those positions. That's the only way this can work. The 1 starts it off and it all ends up ending in the 9. Now what we have to do is fiddle around with a few other selections. I'll put the 2 here and a 3 here, and there's a few other variations, but the 4 we have set in this case to go in the middle. And then the 2 and the 3 I will set here. And other scenarios I will do later. So this is sort of my starting point. All right, so now what we have to do is figure out how many variations are there for each of these. The first 3, I'll put the 8 here. And the next 3, I'll put the 8 down here. And now for the remaining 3, I've only got 3 numbers left, so I can arrange them in, I guess, 3 different ways. Either 5, 6, 7 here. Either 5, 6, 7 like that. Or 5, 6, 7 like that. All right, that takes care of those. And then the ones where the 8 is in the bottom, again, either 5, 6, 7 like this, or 5, 6, 7 like that, or 5, 6, 7 like that. Okay, and then now the next 6, the good news is that you have something called diagonal symmetry. And diagonal symmetry makes your life very easy, because all you have to do is just flip it in the diagonal. And if you do, you get the next set of numbers. So I'll just do the first couple and you'll see what I mean. If the 1, 2, 5 were here, it'll now be here, diagonal symmetry. If the 1, 3, 6 was here, it'll be 1, 3, 6 here. The 4s and 9s don't change, but then the 8 and the 7 do. So you see how it diagonal symmetry just flipped that? And very similarly with diagonal symmetry, you can just get the other ones. I'm just taking the next one, which is right here, and just kind of doing a mirror reflection like that. So 1, 2, 6 goes there, 1, 3, 5 goes there. The 4 and 9s don't change because they're right on the diagonal, but the 7 and 8. So you can do that for the other 4, and I'll just write those in. So there you go. So how many did we get? We got 12 here, right there. So far so good. Now we got to go with the ones where the middle number is a 5. All right, so let's draw some of those. And as before, the 1 and the 9 have to go in those spots. That is the only way this will work. But now the middles are 5s like this. And we'll put in the first few scenarios. This is the first scenario. This is another scenario with the 3 there and the 8 down here. And this is another scenario with the 3 and the 8 here. And here's another scenario with the 3 there and the 8 over here. And the good news is that since you only have 2 empty, sorry, there should be an 8 here, like this. So the first one, there's only 2 missing, right? There's 6 and a 7 missing. So the scenarios are 6 and 7 here, or a 6 and a 7 there. So that means for this first guy, there's 2 possible choices. For the next one, there's 3 digits missing, and those 3 can be arranged in 3 ways. For example, the 4, 6, and 7. So you can have 4, 6, and 7 like that, or you can have the 4, 6, and 7 like that, or you can have a 4 and the other 2 like that. So as you can see, there's 3 ways of doing that. Similarly, since there's 3 here, there's 3 ways of arranging the missing numbers, and here there's only 2, so there's 2 ways. Well, actually here it's a little tricky because there's only a 6 and a 7, so really there's only 1 way of doing that. So that's a little tricky, I think. So if you add these up, you get 1, 2, 3 plus 6, which is 9. And again, by diagonal symmetry, you will get an additional 9. So this scenario, you get 18. And then when the middle is 6, the good news is that, and I'll let you figure this out, I don't want to go through all this all over again, this whole thing, is that it's pretty much the same as case number 1. These guys. Pretty much the same. And because it's the same, it produces 12. So there you go. These are the grand total, 12, 12, and 18, and that is 42. So the answer to number 23 is D. A high school basketball game between the Raiders and the Wildcats was tied at the end of the first quarter. The number of points scored by the Raiders in each of the 4 quarters formed an increasing geometric sequence, and the number of points scored by the Wildcats in each of the 4 quarters formed an increasing arithmetic sequence. At the end of the 4th quarter, the Raiders had won by 1 point. Neither team scored more than 100 points. What was the total number of points scored by the 2 teams in the first half? Let's talk about this question. We have quarter 1, quarter 2, quarter 3, and quarter 4. 2 teams, we've got the Raiders and the Wildcats. Now, the Raiders, they have a very interesting points in terms of their 4 quarters. Those points form a increasing geometric sequence. So that is of the form A, AR, AR squared, and AR cubed. The Wildcats, their points in the 4 quarters form an arithmetic sequence. So they're of the form A, then A plus D, then A plus 2D, and then A plus 3D. Now you say, well, how do you know they're both A? Because they tell you that. At the high school basketball game between the Raiders and the Wildcats, they were tied at the end of the first quarter. So at the end of the first quarter, they have the same scores. That's why I know both of them are A. They want me to find the total number of points scored by the 2 teams in the first half. So adding up these guys, that is what I have to find. All right? So that's the setup of this question. So one more piece of information that is very important, that at the end of the 4th quarter, the Raiders had won by 1 point. So that means that this, whatever this is 1 greater than this. All right? So if we write it out, that means A plus AR plus AR squared plus AR to the power 3 is going to be 1 more than that sum, which is A plus D, A plus 2D, A plus 3D, and then plus 1, right? Because they won by 1 point. So that's our equation. Okay, so how do we go from here? Well, first let's see what we can do here. Anything that we can collect in terms of like terms. If I can factor this, which I can, I get r plus r squared plus r cubed. And this side, I think I can collect a few like terms at least. 4a plus 6d plus 1. Okay. Now at this point, where do we go? This is where I think most students will get stuck. There's a word in this question that I think is helpful. Increasing. Increasing geometric sequence. What that basically means is that r is greater than 1. Okay? R can't be equal to 1 because it's increasing. If r was equal to 1, it would be exactly the same. So r is greater than 1. So that means, I don't know what r is, but let's just say it's 2. I know for a fact that it's got to be pretty small because they tell me quite a few clues that neither team scored than 100 points. So that means that when you add up these guys, it has to be less than 100. So the numbers are not going to be too outrageously big. R can't be like 7 or 8 or whatever because that's going to make it huge. So let's just see what happens with r equals 2. If it's wrong, we'll try something else. If r is equal to 2, I get 1 plus 2 plus 4 plus 8. And this just, not much has changed on this side. Nothing has changed actually. This is just 4a plus 6d plus 1. This side is now 15. So 15a is equal to 4a plus 6d plus 1. And I can bring the 4a over to give me 11a is 6d plus 1. Now, can I get integer solutions for this? Because that's what I need. These are points. They obviously have to be integers. At this point, we really have to do this by inspection since we only have one equation. If we had two equations, then we could solve, but we don't. By inspection, looking at this, plugging in some numbers, I get integer solutions when a is 5 and d is equal to 9. It would be 6 times 9, which is 54. 54 plus 1 is 55. The other side, it would be 11 times 5, which is 55. So there we go. So that means I've got all my values, really entirely by inspection. So now I can just go back and figure out this sum right here that I put a box around. I think I can do it on the same screen. That is going to be a plus ar plus a plus a plus d. So that is 3a plus ar plus d. 3 times a is 5, plus a is 5 times r, which is 2, plus 9. So this is 15 plus 10 plus 9, and that is 25 plus 9, which is 34. There we go. 34 is the answer. Therefore, number 24, the answer is choice E. Let a be greater than 0. Let p at x be a polynomial with integer coefficients such that p at 1 equals p at 3 equals p at 5 equals p at 7 equals a, and p at 2, 4, 6, and 8 equals negative a. What is the smallest possible value for that a? Okay, where do we go from here? Well, one thing I immediately noticed is that if you were to take each of these, right, for example, p at 1 is equal to a. And if you rearrange that, it just means that p at 1 minus a is equal to 0. Correct? And very similarly, you can do that for every one of those. P at 3 minus a is equal to 0. P at 5 minus a is equal to 0. And p at 7 minus a is equal to 0. All right? So what we can immediately do is introduce a polynomial. Let's call it r at x, and we'll call that p at x minus a. And since p at 1, 3, 5, 7 minus a equals 0, that means that this polynomial has roots when x is equal to 1, 3, 5, and 7. So, since those are the roots, we can write it as follows: x minus 1, x minus 3, x minus 5, x minus 7. Correct? Now, those are not all the roots. I don't know what all the roots are. I just know some of the roots. So I can't just leave it at that. I also have to tag on a q at x, where q at x represents the remainder of the polynomial. I have no idea what that is. So keep that in mind. All right, where do we go from here? Well, we know that this r at x is p at x minus a. So let's just put that back in, because that's going to be very helpful for us, and the rest remains the same. Okay, now we're going to have some fun. Now is where we substitute these guys. P at 2, P at 4, 6, and 8. So when we do, we will get some interesting results. First, let's do P at 2. If we substitute 2 for x, we get P at 2 minus a is equal to 2 minus 1 times 2 minus 3 times 2 minus 5 times 2 minus 7. And then we have q at 2. And that is equal to minus a. Correct? So we have minus a. But I'd like to actually get a numerical value, so I will. When you do all this, numbers, whatever, you get minus 15 q at 2 is equal to minus a. But be a little careful, because remember, p at 2 is minus a, but we are actually subtracting another minus a. So this is actually minus a minus a. So it's actually minus 2a. Not that it makes a big difference, but just to be complete and accurate. Now we do the exact same thing for p at 4. P at 4 minus a, we'll substitute that in. And if you do the math here, you get 9q4 is equal to minus 2a. And then, of course, we'll do the exact same thing for p at 6 and p at 8. And that is again going to be minus 15q6 is equal to minus 2a. And then finally, we do p at 8 in the exact same way, minus a, using this same equation up here. And if you do the math there, you get 105q8 is equal to minus 2a. All right. So what did we get here? We have a whole bunch of formulas. We got the first one, which is minus 15q2 is equal to minus 2a. Then we got 9q4 is equal to minus 2a. Minus 15q6 is equal to minus 2a. And 105q8 is equal to minus 2a. So all of these are equivalent. Now, for all of those to be equivalent, that means that these guys are all equivalent. Correct? So to figure out a, we really have to figure out the lowest common multiple of these numbers, which are 15, 9, 15, and 105. That's what this boils down to. Well, 15 is 3 times 5. 9 is 3 times 3. 15, of course, again, is 3 times 5. And 105 is 3 times 5 times 7. So the LCM, 3, we would have to use it twice, since it appears twice. We have to use it as maximum amount of time it appears. The 5 only appears once, and the 7 only appears once. So that is the LCM, 3 times 3 times 5 times 7. And if you do that, that is 315. And that is the minimum, because A is going to be something times 315, 315n perhaps. And this is minimized when n is equal to 1. And that, of course, gives a value of 315. So the answer to number 25 is B.